Good morning, everyone. Thank you, Odin, for the introduction. I would also like to thank the organizers for the opportunity to present my work. This is joint work with both my supervisors, Kerry Morgan and Julian Yuan. So this talk today really is about an algorithm to reduce graphs to a much more manageable size. We then want to use this reduction to find a maximum clique that otherwise is too large to compute or just takes an infeasible amount of time to find. Our reduction here adapts a similar concept to that of the K-core, but with additional elements that arise from our previous work. Okay. Okay, so an overview of today's talk. I'll first give some terms and also background necessary for the reduction algorithm, and then also to show how our algorithm performs on real-world networks. Okay, so we know what a clique is. A clique of order k is just a complete subgraph on k vertices. Often throughout this talk, you'll hear me use the term k-clique instead. And also I'll be using the term belongs to quite a bit. So in this, we'll use an example to illustrate. So in the figure, we'll say that the vertex V1 that's colored in blue belongs to the triangle or the three clique V0, V1, V2, but it does not belong to the three clique or the triangle V0, V2, and V3. And similarly for an edge, we say the edge E2 belongs to both three cliques, V0, V1, V2, and also V0, V2, V3. And we also can say same thing for E3, it does not belong to the triangle V0, V2, V3. I'll also be using the notation here for an induced subgraph. So we use this notation that if G1 is an induced subgraph of G, say. All right. So what is the maximum clique problem? The maximum clique problem states if for any graph, what is the largest clique or the maximum clique that can exist in G? This problem is known to be an NP-hard problem. And while this is a very well-studied problem, there are some existing algorithms that either take way too long to compute, or in some cases, it doesn't necessarily find the maximum clique. So there are many approaches to this. Some people use an approximation algorithm or even just to find a maximal clique rather than the maximum clique. So then before I get into the reduction algorithm, I'll give two new concepts that was first introduced by us in a previous work that was used to generalize the Rich Club. These two new concepts are the vertex participation and the edge participation. So the vertex participation is the number of our cliques that a vertex belongs to. And similarly for the edge participation is also the number of our cliques that an edge belongs to. I'll use a figure to demonstrate. So using this from the previous slide, you notice that for the vertex participation, vertices V1 and V3 have vertex participation 1 in a three clique, and in vertices V0 and V2 have vertex participation 2 because they belong into two triangles. And we can say the same for edge participation. You can see it's quite easy to see E1, E3, E4, and E5 all only belong to one triangle. And for E3, it belongs into two. Okay. And another important concept that is required for the reduction algorithm is the concept of the K-core. So what is the K-core? The K-core is just the maximal induced subgraph where all vertices in the subgraph has degree at least k. We'll again use a figure to illustrate this example. So on the left of the figure, we've got a graph. And on the right, we find the three core. So what it is we're removing vertices with degree less than 3. And this is quite a baby example, so you don't really see much of a reduction happening here. We've only removed two vertices, 9 and 10, which is quite trivial. Okay, next, some facts. that are necessary for the reduction as well. Any K vertex subset of a complete graph also induces a complete subgraph. And if we use this fact, we know that in a clique of order K, then we'll have K choose R cliques, for R has to be smaller than K. And there are also these two trivial facts. If an edge or vertex does not belong to an R clique, then the edge or the vertex will also not belong into a complete graph of order K, right? But R has to be smaller than K. Okay, two useful lemmas. So there's a threshold for both the edge and the vertex, with the edge participation and the vertex participation respectively. So if an edge doesn't meet the edge participation threshold, then we know it doesn't belong into the K clique. Similarly for a vertex, if it doesn't meet the vertex participation threshold, then it also does not belong into the K clique. Okay. Now, here is the graph reduction algorithm. The reduction algorithm here has a pre-processing step for us to find the values of R, K, and also the edge participation and vertex participation. So what the R is really we just first count the number of R cliques in G, and we will determine which R to use based on how long it takes to count these number of R cliques. So we'll stop for R being really small, say maybe it could go up to 5 or 6, depending on how large your graph is. And then we use these counts to find the edge participation of order R and the vertex participation of order R. And we'll also use these counts to estimate what the maximum clique might be. So this will give us the value of K. And with this whole reduction, we use the assumption that the K clique must exist, right? And so for the reduction, there are 3 main steps. For the first step, we remove edges that do not meet the edge participation threshold. And then in the next step, for step 2, we remove vertices that do not meet the vertex participation threshold. And then once we've done step 1 and step 2, in the final step, we find the K-1 core of the reduced graph from step 1 and step 2. And this reduction will result in what we call a K-nup. Use in a figure to illustrate this example. So we use the same graph from before. So we've got graph G that we start here on the top, all right? And the first step is to remove edges. So here we count R is equal to 3. So we look at the 3 cliques. In the first step, we remove edges that don't that have less than edge participation less than 2. So you can see I've removed quite a few edges from here. And then in the next part, we then remove vertices that have vertex participation less than 3. So we've got rid of quite a fair bit of vertices as well. And then in the final step, we find the 3 core or the K-1 core because we assume K is equal to 4. We assume a 4 clique exists in this graph. So in the final step, we remove, we find the 3 core, which is a recursive process that removes all vertices that have degree less than 3. And that gives us this, what we call the 4-nup here. You can see a side-by-side comparison between the 3 core, which was shown earlier as well, and using our reduction, which significantly removed more vertices than it would in the 3 core itself. Okay, next. So now with this, we give the following theorem to our reduction. I won't go too much details of the proof, but I'll give the main essence of the proof. The proof contains 3 main parts. So first part, we know that any edge that doesn't meet the threshold cannot belong to a K clique. And in the second part, we know that any vertex that doesn't meet the vertex participation threshold cannot belong to a K clique. And in the third part, we also know that the K-1 core of the reduced graph also contains a K clique. notice that in this reduction, we don't actually change the structure of the graph at all. So we only remove edges and vertices. We don't add anything to the graph. So it wouldn't remove anything for or remove the maximum clique in the graph. So the k-1 call must have contain also the k-clique of the graph. All right. Now, what happens then if when we use this reduction and our algorithm returns an empty graph? So remember that we assume that a k-clique must exist for this reduction to work. So if the reduced graph is empty, that tells us that the k-clique doesn't exist. So then what do? We need to find a new k, or a new upper bound for the maximum clique. And how do we find this? In finding a new k, it's almost like a binary search sort of method. We think of the initial lower bound as the biggest R that we've used in computing the R cliques. And then for the old upper bound is the current k that you've assumed in the first round of reduction. And then to find the new upper bound, we just use the binary search method where we keep adding them and halving it. And we keep repeating this process until we find a suitable k. So what it's saying is that if we apply the new the reduction with the new k and say if it returns us the same graph, what it's saying is that the k value is too small. So we're not reducing the graph at all. And then we just repeat this process until we're able to find some sort of reduction. And you eventually be able to find the k that gives us the best reduction. All right, so we have experimented this on a real-world social network data. This was obtained from an open source from Snap. Here's a summary of the social network data where there were about 4,000 vertices and the density was at about 0.01, pretty sparse as we expected for a social network graph. And when we after we ran our reduction algorithm, we're able to significantly reduce the graph from 4,000 vertices to 127. And it was a very, very dense graph as well. And we're able to find a really good bounds on the maximum clique, which is roughly about 69. And there are some cases where when we ran the reduction algorithm, it gave us the exact maximum clique. So when we tried this on other different social networks as well. Here, there's one where we've got about 3,900 vertices and the other 2,500. And the good thing from the source is that it gave us a lower bound on the maximum clique. And you can see as well that these graphs are fairly sparse. So using our reduction for the graph G2, we were actually able to reduce it down to the same size of the maximum clique that they were suggesting. And the density of the reduced graph was 1, which suggests that the reduced graph is actually just the maximum clique itself. And then for G1, we're also able to reduce the graph by quite a bit and giving us a really dense graph as well, but not the exact same size as the lower bound on the maximum clique, but still pretty close, but 61 and 57. All right, so it can be seen, it's quite promising. Our reduction actually reduced the graph from 96%, 98%, 99% for all 3 graphs. So very high value of reduction. And also we're able to find either the maximum clique or the bounds on the maximum clique within a really quick computation time as well. We also did try this on some random graphs, but what we noticed was that the reduction works well on random graphs as well, but it sort of prefers graphs with these sort of clumpiness because it reduced it way more than it did with random networks. Future work. So here we looked at only cliques and finding complete graphs. We would maybe try and apply the reduction method on almost complete graphs. So perhaps if we have like 1 or 2 edges missing and see how that reduction applies. And maybe also to look into using the reduction algorithm on the k-core. So we first get the k-core of the graph and then reapply the reduction algorithm to see if we can or are able to sort of further reduce the graph any better or get any more information from this reduction. And yeah, that's it for the talk. Thank you very much.
Thanks, Sue.
Thank you.
Does anyone have any questions? Yep, Jeremy. Did you want to just unmute yourself?
Yes, that would be very helpful. Nice talk, thank you.
Thank you.
I just have a question about, you said there was a case where the end result was an empty graph?
Yes.
Is it possible to be not empty, but smaller than a k-clique? And does that have any implications?
No, that wouldn't be possible. Just because we've got the, so what's it called? The threshold here. Let me find it. Yeah. So these are the thresholds. So we know that for any k-clique, there has to be exactly k choose R cliques in there. So we've got this bound. So then we will not get anything smaller during the reduction. Yeah.
And also, sorry, when you were talking about your results with the reduction, is it, I'm not sure if I'm understanding it right. Besides this method that you were doing, the original one was just taking the k core or the k-1 core. Is that the approach? So this is a new approach to help find the maximum cliques, and you were reducing.
Yeah.
Before this one was the original attempt, I guess, they would just take the k core as a reduction to find the cliques?
I suppose k-core was one of the sort of reduction, not really necessary to find the k-cliques, but we're just using this as a new approach.
Yeah, so I'm just wondering, how does it compare to the old approach?
So what we're saying is, okay, so if you notice with the k-core itself, it doesn't really reduce the graph as much. I know this is really just a baby example, but you notice it doesn't really reduce the graph as much and as quick. I think that, if I'm not mistaken, the k-core was also in NP hard. I don't recall the time complexity of it, but for our ones, we're able to further reduce it to a much more smaller size.
Yeah, I was just wondering though, if the graph was sparse, I thought maybe the k-core might reduce bigger than what that example is.
Suppose.
So that's why, if you don't know, that's fine. I was just wondering how much more this reduces compared, because you have you're kind of showing how much you're reducing it, and I was just wondering how much would it be reduced already just doing the k-core.
Just like, yeah, sure. I'll probably be good to put a side-by-side comparison. Yeah.
Yeah, it's fine if you don't know. I was just curious.
No, don't have an exact answer for that.
That's all right. Thank you.
Yeah, that will be a good idea to put in. Thank you.
Hello, I have a question. Thanks, Sue, for your talk, but I was just wondering how you choose K at the very start, because you talk about K-core. How is K related to like the size of the graph, or sorry if I missed that at the beginning.
Oh no, that's fine. So let me find the slide. Where is my facts? Okay, so if there exists a okay, so we have the counts of all the R cliques for R relatively small, right? So we could probably count for R up to 5, can count the number of K5s or even like K6s, complete graphs of these small orders in the graph. And then what we do is we'll assume, so say if we have a K, we use these counts, and if we assume that this is some value of K, then we take K choose R and compare it to the counts that we have. So if this K choose R value is way bigger than the number of counts that we have, then we can't have that K clique exist. Does it make sense?
Oh, okay, right. So we just have to pick.
Yes, we pick
the
based
biggest
on
K possible. Yeah, okay.
Yeah, that will fit with our counts of the R cliques. Yeah.
Right. Awesome. Cool. That makes sense. And another question I had is, you mentioned like, oh, this runs in reasonable time. Can you elaborate a bit more on the time complexity and also how this compares to existing algorithms?
So our current, the algorithm, it runs in bigger of n plus m. So number of vertices and number of edges in the graph. We've run this and we've actually timed the algorithm as well when we ran this on graphs. So in this one here, let me find. So the reduction doesn't take that long. So once we have all the pre-processing steps done, the reduction takes merely a few minutes to run. Pre-processing it depends on our cliques, I suppose, like how long it takes to count the R, but K3s and K4s are quite quick. So I would say, doesn't take more than a few hours if you're running on these relatively big graphs. Yeah.
Yeah.
Yeah. And we've got more comprehensive details of the time taken in the paper, but it's currently still in process before it's submitted to the archive.
Cool. I'm excited to read it. In this
you.
example here, for the Facebook data, what K value did you use?
We use 126. Yeah, so we chose the K based on the counts that we have. Yeah. And we used the K-choose-R method to pick what K could be, the largest possible K. And then we did the reduction based on that K.
Yeah, that makes sense. Very cool. Thank you.
Thank you. Any other questions? If anyone has any type of graphs you could suggest that we could use to apply our reduction on, that would be great as well. Apart from social networks, it'll be interesting to see how this performs on like other different types of networks. We've tried this on random graphs, but I'm open to any sort of other graphs suggestions as well, if you have any.
Sorry, another question. What's the largest graph you've tried to run this on?
So for the sake of this paper, we actually just tried to keep it at 4,000 to compare it to the Facebook data that we have.
Yeah.
So that's currently the biggest one we've tried onto.
4,000.
Sorry, one last question. With your random graphs, are they also quite sparse, or have you tried denser graphs?
We tried it slightly denser than the 0 points, because what I noticed with the random graphs, when it was too sparse, it didn't really do anything.
Yeah.
So then we tried to keep it a bit more dense, so 0.1, 0.2, but not anything higher than 0.5.
Okay, is that common with real world graphs? Is that why we keep it sparse? I don't know much about very large graphs. Okay.
Yeah, social network graphs are generally quite sparse.
Right.
And they're quite clumpy. Yeah.
Yeah.
This way.
Awesome. Thanks, Sue, for the talk.
Thank you.